far everything went very smoothly with the online presentations.
I think we've had some technical glitches, but I think all the talks managed to be delivered one way or another, so that's good to see.
So yesterday, about this time, a little bit later, we had terrible thunderstorms, and I lost all the connection, all the internet, and I think, oh, hopefully it will not repeat today. Things like that can also happen.
Yeah, we had some of that here as well. Probably got hit by the same thunderstorms.
Probably. Okay, I think it's time. Welcome everybody to the next session. I am Teresa Przybyska, and I will be the chair for the next session, which just includes for your questions at the end of the talk. After the end of the talk, I will read those questions to the speakers. And then, now without further ado, I would like to introduce the first talk and first speaker. So the first talk of the session is a mixture model for signature discovery from sparse mutation data. And the speaker will be Itai Saison. Please, Itai.
Okay, so can you see my screen?
Yeah, we can see your screen and we can see you, so I'm muted.
Okay, so so I will present our model on probabilistic model for sparse mutation data. For convenience, you can use the QR code on the bottom left to open the online version of the data. Okay, so first of all, what is a mutation? A mutation is an alteration of the genome. It could be an insertion, deletion, or a base substitution. As commonly used in this field, we will only look at base substitutions with the immediate left and right context of it. This makes a total of 96 categories of mutations. Mutations are caused by mutational processes, which could be both internal, like replication efforts, or external, like UV radiation. In the figure, we see a person exposed to the sun, which is the mutational process, and his genome is altered by C to T base substitution, which is the mutation. Mutational processes are important for precision oncology. For example, in patients with mismatch repair deficiency show significant response to checkpoint inhibitor therapies. Mutational processes has unique signatures, which are distribution over the different possible mutation types. In the figure, we see an example for the UV radiation signature, which consists mostly of C to T mutations. Here are 30 known and well-studied signatures from the Cosmic Catalog. We can relate most of these signatures to known processes. For example, signature 1 is highly correlated with age, meaning older patients have more signature 1 mutations. Another example is signature 7, which is the UV signature we just saw. These signatures were found with non-negative matrix factorization-based model using whole genome or whole exome sequencing data. We will use these signatures as ground truth throughout this work. So, although sequencing technology got cheaper, in practice, it's still too expensive to use whole genome or even whole exome sequencing. Instead, in many places, only a subset of about 400 genes are being sequenced. We call this panel data. Because of this, instead of the usual 6,000 or 100 mutations per sample, we only get around 6. This caused the data to be sparse and arise new computational challenges. For the usual whole genome and whole exome sequencing, non-negative matrix factorization was used. NMF learns low-rank non-negative approximation of the data. So given samples by mutations matrix, we would like to factor it into two matrices, samples by signatures and signatures by mutations. The signatures by mutations matrix is simply the signatures stacked in the rows of the matrix. In the samples by signatures matrix, also called the exposures, each row I can be viewed as how many times each signature acted on genome I. The data in practice is very sparse, with more than 90% of the cells being empty. So if we use NMF, we will still learn the same number of parameters with only a small fraction of the data. To solve this problem, Gulan et al. Developed the model Sigma. Sigma first learns signatures and exposures from whole genome sequencing data using NMF, and then cluster the samples using the exposures. Next, Sigma simulates panel data from the whole genome sequencing and learns a machine learning model to classify panel data into clusters. The features for the model are non-negative least square, cosine similarity, and likelihood measures. Now, given a new sample, compute its measurements and classify it into some cluster. Although this model showed promising results on breast cancer, it has few clear disadvantages. First, the model requires whole genome sequencing data, which is available for only very few cancer types. Second, panel data has higher sequencing depth than whole genome, so the simulated panel data can be best for training the classifier. Third, although it can classify sparse data, it cannot extract new information from it. And lastly, Sigma has many components that are built on one another, and the failure in one could mean a failure to the whole model compared to Sigma directly, but we will compare to two of its components, NMF and non-negatively squared. To get an intuition for our model, we first look at the clustered exposures given in the Sigma paper. In the figure, each bar is a sample, and in the y-axis, we see the fraction of active signatures in each sample. Here, samples are split between 4 clusters and 12 subclusters, and as can be seen, the exposures within a subcluster and even within a cluster tend to be similar. With this intuition in mind, we will try to build a model that learns exposure for each cluster instead of learning one for each sample. Here it means we will learn 4 to 12 signatures vectors instead of more than 500. Before presenting our model, I will first present the multinomial mixture model, which is a probabilistic analog of the NMF. This model will also serve as the basics for our model. So here we have the signatures denoted by matrix E, where EI is the distribution of the ith signatures. We also have a distribution over the signatures within a sample called pi. We present NMF for a single patient, but similarly to NMF, each patient has a unique exposure vector. To sample from this model, we first sample a signature from pi, and then sample a mutation from the signature. We repeat each mutation in the data. The mutations are called the observed variables, while the signatures are called the hidden variables. So, as we don't really know the signatures that emitted each mutation. In practice, we assume the observed mutations were sampled from this model and use expectation maximization to find the best parameters. Our model will be a mixture of MMMs, with short mix. Given L, the number of clusters, and K, the number of signatures, we would like to learn L MMMs that share K signatures, as well as distribution over them W. To get an intuition about the new model parameters, L is the number of subpopulations within the data. For example, it could be the number of cancer types. W is the distribution over the subpopulations. So if the clusters are cancer types, then W1, for example, is the fraction of samples of cancer type 1. To sample from this model, we first sample a cluster with distribution W, and within this cluster, we use the process we just saw for MMM, so sample signatures and mutations. We repeat this for each sample in the data. Now, aside from the signatures, the clusters are also hidden from us. So in total, we learn less parameters with only exposure per cluster instead of per sample, but we do play with complexity as each sample now belongs to all clusters instead of only one. Here again, we use the expectation maximization to learn the best parameters. The main dataset we use for experimentation is MSK impact. which consists of about 6,000 samples from 18 cancer types, with an average of 6 mutations per sample. We will perform 3 experiments with this dataset. First is hyperparameter selection, then signature detection, and clustering the samples. Note that previous studies focused on a single cancer type, but we believe that because our model naturally clusters samples, it could handle pan-cancer data. So first is hyperparameter selection. NMF doesn't have a clear method to choose the number of signatures. And similarly, most clustering methods can choose the number of clusters as well. Because mixed is a generative model, we can use Bayesian information criterion, or in short, BIC, to perform hyperparameter selection. BIC is a method to score a model with a combination of the likelihood and a penalty for a high number of parameters. We range the number of clusters from 1 to 15 and the number of signatures from 1 to 11, and for each pair we train mix 10 times. The minimal BIC score is obtained using 10 clusters and 6 signatures, and as can be seen in the graph, from some point the number of clusters has less effect on the BIC, suggesting the model is somewhat robust to this parameter. Next, we wanted to use the data to learn signatures. For each signature, we report the cosmic similarity with the most similar cosmic signature. In the graph, similarity to the closest cosmic signature, and print the closest cosmic signature next to the signature. We compared ourselves against non-negative matrix factorization and the clustered variant of it, where we first formed supersamples for each cancer type and then use NMF. As can be seen, signatures learned by mix are more accurate than the other methods, with 6 unique signatures above the commonly used 0.8 threshold. The other 2 methods learned 5 signatures with lower cosine similarity, where we put the last one in a circle as the model already learned this signature. When trying to learn more than 6 signatures, we get similar results. When learning 7, NMF and mix have similar results, but mix still seems to be better on 4 out of 7 signatures. When learning 8, clustered NMF is better than NMF, but still worse than mix. Mix seems to drop in performance on the 8th signature, and even then, it is not a duplicate and not a significant fault. The other 2 methods tend to learn duplicate and worse signatures on their own. Another interesting result is that mix and NMF learn different signatures. So NMF learned signatures 13 and 15, while mix learned 4 and 6, suggesting they give a different view over the data. For our last task on this dataset, we used mix to cluster samples. We ranged the number of clusters from 1 to 15 and reported the adjusted mutual information score between the learned clusters and the non-cancer types. The adjusted mutual information takes 2 clustering as input and gives a high score if they are in agreement. For benchmarks, we used k-means and k-means on the mutation catalog and k-means on the exposures obtained by NMF. To cluster a sample in mix, we use the cluster with the highest likelihood to generate the sample. As can be seen, mix gives more informative clusters even when using as little as 2 clusters. And as in the big score, from some point it seems the score doesn't change much, again suggesting the model is robust to the number of clusters. Lastly, we wanted to test the performance of mix on reconstructing hidden mutations. So given a partial mutation catalog, like panel data, we would like to construct the full mutation catalog. In short, we want to construct exposures from sparse samples such that it will represent the exposures for the full samples. The full process is as follows. Given whole genome or all exon data, we downsample it and split the samples into train and test. Using the train data along with cosmic signatures, we train mix. And after mix is trained, we insert the downsampled test samples into mix and insert an exposure vector using two methods. First is hard clustering, where we use the exposure of the best cluster. And second is soft clustering, where we use a weighted sum of all the clusters with weights equal to the probability of each cluster. After this, we multiply the exposures by the signatures, and we get our reconstruction data. We then compare this to the full mutation catalog to get the reconstruction error. This process should mimic a realistic settings where we have some trained mixed model on panel data, and we want to reconstruct the mutations of a new patient. For comparison, we simply use non-negative least square along with cosmic signatures to get the exposures, and from there the process is the same. So for this experiment, we used whole genome breast cancer dataset with an average of 6,000 mutations per sample, and whole exome ovarian cancer dataset with an average of 120 mutations per sample. We reduced both datasets to 24 and 12 mutations, and as can be seen, both variants of reconstruction mix are better than non-negative least square. In particular, the soft clustering approach dominates across all settings. Also note that the performance of non-negative least squares significantly worsened when using 12 mutations, while mix is almost unaffected in comparison. This suggests that mix is better suited for more sparse data. To summarize, we designed mix, a novel probabilistic model for sparse mutation data. Mix learns signatures and cluster samples simultaneously. We showed it outperforms state-of-the-art methods in both signature detection and clustering. We also presented the reconstruction functionality that might be appealing in practice and showed it to be better than the usual non-negative least square. I want to thank my advisor, Tracy Chen from the University of Maryland. I also want to thank Safra Center for Bioinformatics for funding me. And if you have any questions or want to discuss this work, I'm available on LinkedIn under Itai Sasson. And thank you all for your attention.
Thank you, Itai, for this nice presentation. Let me see if there are any Q&A. Yes, and there are some. Mysore Bajati, I hope I did not mispronounce, says great talk. This novel method is designed for sparse mutational data. I wonder if you have tested this model on non-sparse data to see if the known previous result reported in Cosmic can be reproduced.
Okay, so I did try it on the non-sparse data. It seems like, for example, in breast cancer, we managed to construct all the 12 known mutations, but for example, the big score didn't work as expected, as it gave too much clusters. But we did manage to find signatures.
Oh, okay. And just one more question. Hey, I have a question. In the hyperparameter selection, how did you obtain the range of parameters L to be 1 to 15, which indicates the number of clusters, I guess? Thanks.
So it's just a rough guess. We ranged the parameters and found the minimum, and then took around twice as many parameters.
Okay, so there are no more Q&A. So I actually have one more question. So did you try to compare the results on exome only versus whole genome only? Would you get the same signatures? Would that signature be consistent with Cosmic? Would some signature be substituted from the others? How stable that is when you move not randomly from the same distribution, but kind of have a biased one taking from exomes that might behave differently than the rest of the genome? If you look at
no, I did not try to compare all exome and panel data, but the last experiment with the reconstruction error shows that the signatures we get are about the same.
Really? But that one was for random, but I was thinking from exome.
Oh, yeah, so on the journal paper, on the journal version, we will try to compare to directly to panel data. Okay.
Very interesting to see. Okay. So there are no more questions. So and the time is also up, so thank you, Itai. And we'll move to the next speaker. Okay. So our next talk is a highlight talk. The mutational constraint spectrum quantified from variation in 141,456 humans. And the speaker is Konrad Karczewski. Okay, please come.
Great, thank you. So I'm going to talk about work that I've been doing with the Nomad Consortium